Okay, before you start taking notes on these examples for horizontal and vertical asymptotes, you may want to refer back to pages 11 through 12 on the information there about horizontal and vertical asymptotes. In particular, for number 56, but before we even start number 56, you want to look at the my quick method for determining horizontal asymptotes, because this boils down into very simple and portable terms what your book goes into a lot of detail to explain. So we are to find in number 56 all the vertical and horizontal asymptotes of the function. Just like when we were doing domain and I told you to look for the red flags, that you should start with the numerator on rational functions, I'm going to suggest that you always start with the numerator, because the denominator is going to kind of jump out at you. But the numerator you can lose in the shuffle of being so excited that you know all about the denominator. So let's start by looking at where the numerator is involved in terms of the asymptote question, and that is with horizontal. So I'm going to suggest that you always go to horizontal first, because you'll forget, I promise you. Alright, so horizontal asymptotes, that is the question. Well, if you use my method, your first thing to do once you notice it's rational is to pay attention to the fact of the degree of the top versus the degree of the bottom, and that's what I classify as top heavy, bottom heavy, or matching. Well, since the degree of the top here is 1 and the degree of the bottom is 1, this one is one I would classify as matching. And it's technically matching degrees, but you want to keep it short and simple, so matching. So once it is, then you can just look at the leading term, and that's the term with the highest degree from the top, and that's really all you have to do for all of them. But you can put the x over x, because that's where the what I call heavy terms, the highest degree term from the top over the highest degree term of the bottom. And if we put 1s in front of those for emphasis, the x's would cancel and leave us with 1 over 1, which is 1. So that tells us that we have a horizontal asymptote at y equals 1. It's that simple. And it's always just the ratio of leading coefficients for the shortcut there. And then we need to talk about vertical asymptotes. So vertical asymptotes occur wherever the denominator equals 0, unless there's a canceling factor, which we don't have here. The only exception to the denominator equaling 0 tells you where your vertical asymptote is if there's a canceling factor, like one we had in an earlier example in one of the previous videos. So in this case, we see that the denominator equals 0. When I write the equation, because all that's in the denominator is x, I write x equals 0. Then I've already got x isolated. That is my vertical asymptote. So that is my answer. Don't have to do anything with that one. So I know we have a vertical asymptote at x equals 0, because that's where the denominator equals 0. And those are my vertical and horizontal asymptotes. And it wouldn't hurt if you graph it, so I include the graph here. And I say wouldn't hurt, and the reason I word it that way is the directions don't insist that you confirm it graphically, but that's one way to check your work, is if you look at it every time. So let's look at this picture and confirm what we just said. We just said that there is a vertical asymptote at x equals 0, which is right here in the middle of my picture, and that there is a horizontal asymptote at 1, and look what happens when we draw those on this picture. The analysis proved us right by the graph. And then we go to number 60. We'll do the same thing. Same process. We start with horizontal asymptotes. And again, we look at bottom heavy, top heavy, matching. And there is no x term on the top, so that means all the weight is on the bottom, and we can talk more about what that means if that confuses you. But the degree of the top is 0, because I could put an x to the 0 there. So that's a 0 degree top with a 2nd degree bottom. Means it's bottom heavy. And you can actually write that on your tests and stuff for me. You write that for a professor in college, he's probably going to ask you what's wrong with you, or ask you to be more technically correct. But bottom heavy implies that we have a horizontal asymptote at the x-axis, which is, and it would not hurt my feelings at all if you wrote it this way all the time, horizontal asymptote at the x-axis and then put comma y equals 0, because that'll reinforce it for you for various reasons that you would need to be able to refer to the x-axis in that way. Alright, and then the vertical asymptotes, again, we determine whether or not we have one, and if we have one, where it is, by setting the denominator equal to 0. So let's do that now. X squared plus 1. Now this is not as straightforward as the last one, because when I write this, it's not very straightforward because x is not by itself. So let's start by isolating x, and the first step to do that would be to write x squared equals negative 1. Now, one thing, you've been so brainwashed that the goal is to get x by itself that sometimes your brain shut down on you. But when I see this, I stop. Why? Because there is no number that you can square and get negative 1. So I already know there is no solution to this equation, which tells me that there is no vertical asymptote. So when I set the denominator equal to 0 and I start solving and x can't be 0, then I've eliminated the possibility of a vertical asymptote. Well, let's just say you need to solve this out to x by itself to see what I'm talking about. All right, so what would you do next? You would take the square root. Well, look what happens. Now I've got to take the square root of negative 1. Not a real number. No real solution. And you can abbreviate solution that way as well. That's the universal. So from our analysis, we now know that we have no vertical asymptotes for this graph. And again, I'm providing you with a graph to confirm what I just said. And as you can see here, there is a horizontal asymptote where we said there would be one, which is at the x-axis. There is no vertical. On to the last one. And this one you need to be careful on. Now, on the last two we just did, which were 56 and 60, there was nothing I could factor in either the top or the bottom. But in this particular case, there is something I can factor in both. So I'm still writing in straight lines. Getting a little carried away. All right, so let's try that again. Here we go, got a marker. Okay, what can I factor out of the top? I can factor out of 2. When I take 2 out of 2x, I have x left. When I take 2 out of 4, I have 2 left. The top is factored. Then on the bottom, I have a difference of 2 squares, which is x minus 2, x plus 2. And I'm not quite finished with the simplification process because of the fact that I have a pair of factors that cancels. And remember from a previous example I did that I want you to draw a line through them like a slash to show they've canceled, but I want you to turn that slash into an arrow and write what that causes in the graph. And it is a hole at whatever makes that factor 0. Well, what would make x minus 2 0 is at x equals 2. So just make yourself a note of that so you don't do anything silly. All right, and then we're going to switch back to green and finish this out. Because now that I've canceled that pair of factors, what I am left with is 2 over x plus 2. And now, because I know I have a hole at 2, well, that's significant, except for the fact that they didn't ask me to find that. But it keeps me from saying that there's a vertical asymptote, because I know there's not a vertical asymptote at 2 because there's a hole at 2. More on that when we look at the graph in just a second. So let's take what we know. Now that we've boiled this function down to this little simplest form, it's a much easier problem to think about because it's bottom heavy. There's no x on the top, so the top is of degree 0, the bottom is degree 1. So if it's bottom heavy, and I'm going to go to my horizontal asymptote question first, bottom heavy tells me that I have a horizontal asymptote at the x-axis, aka y equals 0. Okay, set that aside. We still got to talk about the vertical. And in this case, we're going to find one, because remember, to figure out whether you have one, you start by setting the denominator. And in this case, is a classic example to show you. You should not do that until you've done all the simplifying you can, or canceling if it's possible, like it was here. So we set the denominator equal to 0 and solve, okay? But remember, when you're setting the bottom equal to 0, if you want to confirm it that way by putting a can't be equal, to write a definitive statement, you can make it not equal to 0. You're just responsible for making sure you know what you're talking about. Then we subtract 2 from both sides and figure out that x can't be 2 in this problem, which tells me that's where my vertical asymptote is, because by definition that's what a vertical asymptote tells us. So we have a vertical asymptote at x equals 2. Now let's confirm that by taking a look at the graph really quick, and here it is. So as promised, we had a horizontal asymptote at 0, and we have a vertical asymptote at -2, which is right here. And remember, the graph lies to us about whether or not we have a hole, because it can't make one. So in essence it's lying because it doesn't know how to tell you that. So the hole would have been at 2, just for future knowledge, and you will need to know this at some point, would happen right there at x equals 2. So, and just for emphatic purposes here, I'm going to try to make it match the background behind it to show that there's a hole there. And there it is.